the second day of our conference of biomass to chemicals and fuels. And this morning we're going to move into the more scientific and more technical part of the conference. And we're going to start at the beginning, because the beginning is the best place to start. And Bill McCutcheon from Texas A&M, who is Deputy Associate Director of the Texas Agricultural Experiment Station, is going to talk to us about plant biotechnology and feedstock engineering. Bill?
Do we have a laser pointer? I was told we did. Yeah. Can everybody see that?
Yeah. Yes. This is good.
Okay.
You don't have to dim the light to begin.
Read.
First of all, I want to say thank you for the organizers for inviting me. Thought the discussions yesterday were very productive. In the morning and the semi-roundtable in the evening livened up the debate on where biomass and biofuels and other products are headed, and it's going to be interesting to see over the next decade or so to actually see where we end up in this area. And with that, I want to talk about plant biotechnology. And as I thought through this, what to present here, I thought, based on my history, well, let's put it this way. I was on the dark side 6 months ago working for DuPont and Pioneer, overseeing some genetically modified crops research. And I thought the best way is to take an example, and I'm going to use one of the examples we have at Texas A&M University. And actually, we've been working, 10 years ago, A&M started working on high biomass and high energy sorghum crops. And I thought I'd utilize that as a platform for how biotechnology and applied genomics can be utilized to, as the talk says, to engineer these feedstocks for biomass. So we're going to go through sorghum, and I'll briefly describe why sorghum, the DOE's bioenergy roadmap. Then we'll move into Texas A&M agriculture sorghum roadmap. I'll briefly talk about an alliance that Texas A&M agriculture and engineering have recently entered into and why that's important to feedstock engineering. And then finally end up with the path forward. So, sorghum. Many of you may be aware of sorghum, and most of you probably familiar with this type of sorghum. It's hard for me to see up here, but the grain sorghum, which when it's mature turns red and is harvested primarily as a feedstock in animal feed. But in any case, biofuels and biomass all of these crops that are going to be developed and are being developed are going to be on a regional basis and where they fit within the ecosystem. We just happen to believe that sorghum is a logical feedstock, if not a particularly premier feedstock for Texas and beyond. This just gives you an indication of where sorghum is being grown today, and this is grain sorghum. This does not include the forage sorghums and others. You see a high concentration here in these Texas states. Actually, yeah, that's Oklahoma and Kansas and Nebraska. But this map would look a lot different if this was about 10 years ago. The amount of sorghum in Texas has actually decreased, and we touched on this yesterday. That's because of a lot of the farm subsidies. Producers tend to plant corn now in these locations because if you happen to run into a drought situation, the return on for a corn subsidy is much higher than that of a sorghum subsidy. And that's, well, I won't go into that, but anyway, that's basically the map of where sorghum is grown. It can grow in many different places and has a lot of potential. The three different types of primary sorghums that we're looking at Texas A&M include grain, which is your typical sorghum that you see alongside the road. That can be grown, again, as an animal feedstock, can also and is being utilized for ethanol production. Sweet stalk sorghum, which is basically analogous to sugarcane, can also be grown as a source for ethanol. And high biomass sorghum, which is what we believe to be a very good, let's say, has a lot of potential for being a high biomass lignocellulosic raw material. Again, it is a dual feedstock for livestock, and it's a win-win for rural communities and the sorghum industry. As I grew up in Central Texas, and I can remember there were basically only two crops at that time prior to subsidies, and that was cotton and sorghum, and they were exchanged and planted across Central Texas and through various parts of Texas. Now, I just want to point out some of the reasons why we believe sorghum is indeed a potentially premier feedstock. And one of the things we talked about a lot yesterday was water. And I think water and energy go together in a lot of different ways. And one of the aspects that sorghum has, as we see here, these are 4 different types of sorghum, including hay grazers, photoperiod sensitive, and BMR sorghums, and this is compared to corn. Now, this is tons per inch of irrigated water, and what we see here, and Bill Rooney and others have been conducting these tests for the past 5 years, is that, excuse me, sorghum has the potential to produce twice the biomass with one-third the water. So if we're talking about areas where you may have particularly, excuse me, areas that are prone to drought, and also just aquifers that are dropping, such as we have in the panhandle of Texas, sorghum presents a very viable opportunity for the bioenergy platform. And while I was working at DuPont, one of the areas that we were focusing on, and to include nitrogen utilization, was drought, and are commonly referred to as water use efficiency. Drought is composed of many different traits and genes, but it is expected to be one of the premier plant biotechnology traits in the future, along with nitrogen utilization. Now, key advantages of sorghum include, of course, high yield and drought tolerance. We're seeing about 15 to 20 dry tons per acre, which is fairly significant. This is with some of the high biomass and sweet sorghums. We believe through crop modeling, and as we do further research on how this is planted and harvested, we can move that tonnage up. The other thing about high biomass sorghums is that they're a ratoon crop. In other words, it's just like cutting your lawn. You can go out, harvest the sorghum, and it regrows, and Within the Texas area up through Oklahoma, you can get 3 cuttings per year. So it's a matter of harvesting, probably applying some additional fertilizer, and then going back and harvesting again. I'll emphasize this one more time. On a per unit basis for water, we conservatively see 33% more biomass than corn. And as we talked about corn yesterday, we feel like sorghum is well positioned, especially in areas where row crops are traditionally grown. Also, and what's very exciting is that there is a current genome scale research being conducted that is looking at drought tolerance mechanisms, as well as yield, insect and disease tolerance. And again, having come from the dark side, we know that genomics are going to play a very major role in how crops are developed in the very near future, and not just through genetic engineering, but by knowing the genome of these crops, you're able to do molecular breeding. And so your traditional breeding can now be expedited by knowing where genes are within the plant and being able to match those genes up as you do molecular breeding. Now, DOE's Bioenergy roadmap, I'm not going to go through all the detail here, but I think they've laid out a fairly comprehensive roadmap to include integrated bioenergy and crop process research. And we'll get into some of the details of this morning, but as I just mentioned, the genome of these plants is an incredibly powerful tool. You'll be able to look at things like enzyme interactions, look at tolerance and control of, for example, sugar and starch production, and the basic overall strategy for systems biology to biomass, whether you want to produce a certain type of alcohol biofuel and or other products. So without going into, again, a lot of detail, we see here that the roadmap is laid out over 15 years. We believe that we have some technologies, and in fact we're starting with sorghum to enter into this phase, and I'll briefly talk about a microbial conversion process that's been developed at Texas A&M, that we have pilot production plants, and we're getting ready to, and hopefully in the near future, to develop a demonstration plant that will convert this biomass into mixed alcohols. Now, I noticed this was presented a couple of times yesterday, but this is a little different format, and again, this is the fossil energy ratio, the energy delivered to the customer and the amount of fossil energy used. If we look at electricity, gasoline, and corn, and there's some discussion about this, but currently these are the projections. However, we do see this quantum leap here in cellulosic ethanol and biorefinery, projected to be around 10.3 for the FRE. So that really does provide a paradigm shift if we just use this as a target, and we can use the entire plant instead of just the grain from and starch from sorghum and corn and other crops. If we move towards energy crops like high biomass sorghum, I think we can start to creep up on that 30% that we're expected, or what the government has given us as a goal to reach in the next 20 years. Of course, this includes a lot of integrated science. I won't go through all of this, but it includes feedstock and cell wall deconstruction, feedstock engineering, which we're discussing here today, fermentation, all of this science has to be integrated. And to take that on, it's going to take more than a Texas A&M. It's going to take more than a Rice University. It's going to take industry. The energy companies are investing in this. It's going to take the national labs, the MITs of the world, because I can tell you that having the genome and basically the roadmap for how these plants basically function on a day-to-day basis is an incredibly powerful tool. And again, you're going to start seeing a lot of this research first come out in corn and soybeans, because the corn genome has been completed. The soybean genome is near completion. And a lot of traits for disease, nitrogen utilization, drought, those hybrids are actually in the pipeline to be released in the next few years. And again, that's not genetic modification. That's basically taking the molecular roadmap and being able to see, at least as far as your headlights, where you want to go in the next 5 to 10 years. Now, the quandary that we have, and I think we'll be discussing a lot of this today, is lignin, cellulose, and hemicellulose. Having a basic understanding of these variables and how we utilize this for biofuels and other products is, I would consider, probably one of the larger or biggest challenges to making lignocellulose and the production of biofuels. Well, it's certainly one, if not the biggest challenge. And we're starting to conduct research in this area around sorghum. Again, why are we choosing sorghum? We are, as well as other institutes, are putting in the genetic platform. The genome will be finished sometime in the first or second quarter of this year. And that genome is going to allow us to increase the yield of sorghum, grain, forage, and lignocellulose inbreds. It also allows us to look at things like drought tolerance and other environmental conditions. And sorghum is particularly, let's say, favorable in marginal land areas where you may have drought or other conditions. And finally, we seek to optimize sorghum's biomass composition for downstream conversion into biofuels and other products. This is just some of the platform that's being assembled at Texas A&M and other institutes. A lot of work and funding has gone on. This represents the timing of the funding. But as you can see, genetic map, the physical map, cytogenetic maps, just an incredible array of genomic information. And based on my experience, we're about 4 to 5 years behind corn and a couple of other crops, but the platform for sorghum is going to be there, and the sorghum genome sequence, like I said, is going to be finished early in 2007. And based on what's been learned and developed in corn, there's a lot of potential here to develop sorghum as a premier biomass for lignocellulose biofuels. Now, without having too much time to go into detail, one of the primary way this is done is genetic or G/E studies. And so a lot of this work can be done in the greenhouse, but once you have let's say a variety, a line, a hybrid of sorghum, for example, you can do detailed analysis in the greenhouse or in the field. You can identify phenotypically the types of traits you're looking for. This is fairly severe, but this is the detail type of detail to control that environment that you may need to go to. But basically, by taking the field data and comparing that to using microarrays for gene and protein expression and looking at the biochemical pathways, you can start to elucidate the genes responsible for certain traits like drought, biomass, yield, insect resistance. And the other nice thing about this is you can make comparisons of sorghum with corn, rice, Arabidopsis, and these other model systems. And this is, again, I can't overemphasize the power of this technology. And in fact, at A&M, Dr. Mullett, Drs. Rooney, and several others have in fact identified 5 QTLs, quantitative trait loci, associated with drought, and are now in the midst of characterizing these further. And since I'm responsible for intellectual property and technology commercialization, you can be guaranteed these traits are being patented, and the Monsantos and DuPonts of the world are actually interested in looking at these drought traits to see if they can find analogs in corn. And we're in discussions with them right now, but basically by having these genetic maps, the physical maps, we can over time get down to a small area and actually identify the genes and the promoters. You can actually see when these traits are turned on and off due to environmental responses and stresses. And as I said, this looks fairly complex, and it is, but through genetic environment studies, you can get down to the particular genes or set of genes that are actually responsible for providing, in this case, sorghum, a level of drought tolerance. Now, with this said, we believe that sorghum is in fact indeed a premier source for biomass, and we don't have any question in our mind that it's certainly much better positioned over corn, as well as studies that we've done with switchgrass in terms of its overall potential to produce biomass. It's drought tolerant, it's a low input crop, it does not require a lot of fertilizer, herbicides, and has fairly good characteristics for insect and disease tolerance. We have an incredibly diverse germplasm. Hybrid vigor is excellent, and the genome of sorghum is relatively small compared to other crops, especially to things like switchgrass and other crops. Again, the genome technology platform is being established. The biochemical pathways and genetic engineering is now possible. We have extensive breeding programs throughout the state of Texas, up through the Panhandle, all the way down to Weslaco. And in fact, we are testing sorghum, including the grain, the sweet sorghums, and the high biomass, the lignocellulose. We're looking at utilizing and are conducting studies right now that are in progress. It also has the ability to translate this research, or this genome research, to switchgrass and other biofuel crops. And we believe that sorghum will not only have an impact in Texas, but major portions of the Midwest and Southeast, as well as a worldwide impact. A lot of sorghum's grown in Australia and other parts of the world. Now, recently, Texas A&M Agriculture and Engineering have aligned their resources and research in the area of bioenergy. Not to say that this wasn't happening previously, but we formally aligned in the areas of bioenergy to utilize our expertise. And I'm going to give one example of that, but this basically lays out the strategy, if you will. I know this looks like an org chart, but it's actually a strategy for how we're moving forward in the area of bioenergy. Doctors Morano and Bennett, of course, who are the deans of the two colleges, agriculture and engineering respectively, are overseeing this project. We do have, for example, the Bush School of Policy involved in these discussions, as well as the Office of Technology and Commercialization. So we're working from end to end. We have an integrative ag engineering and policy strategic team. And I wouldn't say we make decisions, but we help provide guidance and help look for resources in these different areas down below, to include plant biomass production and design, alternative biomass development. I wish I had more time, because, but I will say something here. 25% of the nation's beef cattle are within a 250-mile radius of Amarillo, Lubbock area, and when you have 25% of the nation's beef cattle, waste comes along with that. And we're doing a lot of research on cow patties, if you will, and it looks very productive. Gasification and emissions, biofuels processing, advanced technology and systems development, and of course regulatory, economic, and policy issues. This is not a comprehensive list. We've actually broken these groups down further into teams around, for example, we have a genomics team, we have a crop modeling team, et cetera, and so these teams are starting to look at how we fully integrate across ag, engineering, and policy to develop a biofuels economy, and we'll probably start out in the Brazos Valley. The Alliance seeks to overcome challenges with biomass feedstocks, biofuels processing, biomass-enabled reduced emissions. We have a very strong program, not only at looking and characterizing biofuels, but actually looking at the emissions and some of the regulatory variables that need to be looked at. I don't know if you've, well, we have a next generation engine that's also been developed by Mark Holtzapfel called the Star Rotor engine. We're actually testing these biofuels in this engine, as well as looking at these at some of our transportation around the campus. And we're also looking at integrative systems of engineering. Now, almost finished here, but I just will briefly talk about one of the areas that we're trying to link up in this case, these sorghum hybrids with a conversion technology that's been developed by Dr. Holtzapfel in engineering. So we have about 500 to 600 lines of sorghum that we're quickly trying to select the best sorghum varieties based on lignin content, based on overall biomass, drought tolerance, and we're actually using the MixAlco process as another way to optimize this. And now this is a microbial conversion technology that basically can digest lignin, cellulose, hemicellulose, plus the other plant products, produce carboxylate salts, which are then, through chemical processing, converted to liquid biofuels. And this, the reason it's named MixAlco, it actually produces mixed alcohols. And most anything can be used. Trees have been looked at, grass, agricultural residues. In this case, we're trying to optimize this conversion technology with a specific energy crop, and that's sorghum, or also solid waste, sewage sludge, and animal manure. Now, this is just a simplistic diagram. If Mark Holtzapfel was here, he could probably spend 3 or 4 hours talking to you about this, but basically by taking sorghum and sugarcane and going through extraction, we're going to the MixAlco process where we're producing alcohol, fuels, plus other byproducts. For example, acetone. So we're not just looking at ethanol, we're actually looking at the higher alcohols, the butanols, isopropyls, things like that. This is, I wouldn't say analogous, but instead of producing sorghum and sugarcane for the sugar mill, we now have the capability of taking this to produce alcohol fuels instead of sugar. So it's a, we can call it a dual use property, and again, sorghum in itself has the ability to be used as feedstock for animals, but also feedstock for biofuel production. So with that in closing, I'll just say that applied genomics has incredible potential to optimize and look at a number of different things, including yield, water use efficiency. We believe this, again, is one of the major traits that we'll be able to use not only in sorghum but in other crops. We have extensive research going on in disease and insect resistance with sorghum. We're also looking at biomass composition, the starch, sugars, cellulose, hemicellulose, and lignin. We have, in fact, some lignin mutants, and depending on if you can envision, if you will, you may want a certain percentage of lignin within the overall lignocellulose biomass, which may be optimized for the MixAlco system to produce higher quantities of alcohol fuels or other products. Leading into that, biomass conversion. Now, we believe there's a lot of work that can actually be done with the MixAlco system by optimizing the microbes that are being utilized in this system. And we're putting together with some partners a team to actually look at microbes and how they can be utilized in this system to produce the alcohol fuels and other products. And with that, I'll just say that although we're concentrating on sorghum as an energy crop of the future, we see the applied genomics platform being used for other crops to include switchgrass, even corn, if we continue to use corn residues. But the power that the genome brings to the table is just, there's no other way to describe it. I worked with traditional breeders at Pioneer, and now they can take these tests out to the field, and they actually know which plants contain these genes that provide them insights to which isolates they actually want to breed. And this saves a traditional breeder, up to 5 to 6 years of his life by being able to go out and use a diagnostic test. And with that, I will end and entertain any questions if there are any. Thank you.
Thank you, Bill, for the presentation. Are there any questions?
Yeah.
Yes. Can you get the microphone?
Yes. Thank you, Bill, for your interesting presentation.
Thank you.
I have 3 questions. Basically, how many harvests per year can you get out of the sorghum cultivation that you have? If you are interested in alcohol, you probably would concentrate on sweet sorghum as opposed to grain sorghum. And I'd like to have a comment from you on that. And then if you could indicate what are the ethanol yields of the simplest route, not the MixAlco route, but the simplest route of just getting the sugar and the starch contained in the sweet sorghum, for instance. How many gallons of ethanol can we get from a unit mass of the material? Thank you.
Yes. I'll start out with the last question first because I haven't had but one cup of coffee and I forgot the first question. I don't know the exact numbers. We have them, but with some of the sweet sorghums, and I actually made a misstatement. These sorghums were actually started on or being developed during the early 80s, during the first oil crisis, and there were 5 to 6 years of looking at sweet sorghum and high biomass sorghum solely for the purpose of energy production. Now, 6 years ago, Bill Rooney and some others picked this up and started working in this area again, just in case there was another oil crisis. The answer to your question is, if my memory serves me correctly, when sugarcane has been compared to sweet sorghums, I think you're looking at about 80% of what sugarcane can produce. But you have to remember, I think one of the gentlemen mentioned yesterday, sugarcane's the answer. And it absolutely would be the answer, except for one small problem. In North America, except for a few regions around the Gulf Coast and Louisiana, the amount of water to grow sugarcane is immense, and it also likes tropical environments. So the answer to your question is about 80% of what we see with sugarcane. Now, I believe you asked the question, should we be using sweet sorghums over starch, or the grain sorghums? And in fact, we are. These hybrids have not been released yet. They're still, if I'm back in my industrial mode, they're in the development stage and can be ready for release within the next 2 to 3 years. So you're absolutely right. If we're going to produce ethanol, we would certainly want to move away from the grain sorghums to the sweet sorghums because of the overall potential to, well, make grain sorghum look silly. And in fact, we're looking at putting sweet sorghums around a couple of ethanol plants. And my synapse just kicked in, and I think your first question had to do, actually it didn't.
Number of crops per year.
Number of crops per year. What we're looking at right now, at least in the Texas area, and it goes all the way up into the Panhandle, and we believe beyond, is that we can routinely get 3 cuttings per year. But however, we're looking at optimizing, fertilizer inputs. That's also going to be based on, especially in dry land where you're not irrigating sorghum, which will be 95% of the case. It will depend a lot on, water availability, i.e. rain. But 3 cuttings is certainly not out of the question at all.
Well, in the interest of time, I think we should move on, and I hope that Bill can stay around so that we can continue this discussion during the breaks and during lunch. And the next presentation is, thank you Bill again. And the next presentation is going now to start focusing on the crucial pretreatment that's going to make the biomass now ready for the next step, the conversion step. And it's going to be given by Professor Charles Wyman, who is with the Department of Chemical and Environmental Engineering of the University of California at Riverside. His talk is going to be on biomass pretreatment, a vital interface between plant and conversion systems. Charles?
Thank you very much. First of all, I'd like to thank the Baker Institute for inviting me to give this talk. And I'm going to be talking a little bit about pretreatment, which is the interface really between the biological systems of producing biomass and converting that biomass. And on behalf of myself at the University of California, Riverside, but also working with a company called Mascoma Corporation. And let's see if I can figure out how to work this. And that's set against the backdrop of some loons. First of all, I thought what I'd do, shown on Lake Mascoma, give a little background about Mascoma Corporation. It was conceived last summer. It's basically looking at advanced technologies for conversion of cellulosic biomass to ethanol. Initially, it's based upon Dartmouth biological systems. And it's forming partnerships as well to commercialize advanced cellulosic ethanol technologies. And its founders were myself and Lee Lind at Dartmouth College. A little hard to read this in this light, but
I can see it. It's just hard to see it from where you're standing.
okay, I can't read it myself. But anyway, the chairman of the board is Vinod Kushla, who's the founding CEO of Sun Microsystems and been involved in a number of startup companies, including Google. And first round of capital is from Kushla Ventures and Flagship Ventures. And more information is available at mascoma.com. But really, just to focus now on really this pretreatment technology and this interface to unlock low-cost ethanol. If we look at energy use in the United States, we really see that energy supply and demand are pretty well balanced in all but one area, and that's petroleum. And we also use more petroleum than any other energy source. We use about 40% of our energy comes from petroleum. And about 60% of that is imported. So, and if we look furthermore at where does petroleum go, 2/3 goes to transportation, which in turn is almost totally dependent upon petroleum as an energy source, about 96-97%. And in addition to that, if we look at greenhouse gas emissions, the largest source of greenhouse gases comes from transportation as well. So really, if we're going to look at petroleum use, we really have to look at alternative fuels for transportation. In my opinion, also, we should look at sustainable fuels to, A, avoid future transitions. No sense of doing these transitions any more than we have to. But in addition to that, also, sustainable fuels have the attribute of reducing or avoiding greenhouse gas emissions. Now, if we look objectively at sustainable alternatives for transportation, and this is a plot developed some time ago by Lee Lind at Dartmouth College. I've simplified it considerably. It's a massive spaghetti diagram if you put all the different human needs on the right-hand side. But if you focus on the various sustainable resources of sunlight, wind, ocean hydro, geothermal, and nuclear, and then look through what Lee has called primary intermediates of biomass and electricity, and secondary intermediates of organic fuels, hydrogen, and batteries, and we link those routes up to transportation, we see if we want organic fuels for transportation, there's really only one sustainable route of significance that we know of that's really has the potential of low cost, and it's sunlight to biomass to organic fuels for transportation. And we've made considerable progress in that direction, both in the United States and Brazil, where both countries produce on the order of 4 billion or more gallons per year of ethanol. In the case of Brazil, that ethanol is produced from cane sugar. In the case of United States, ethanol is produced from starch crops, and that's primarily corn. And these are certainly have made tremendous progress in terms of looking for routes to sustainable production of transportation fuels. But there are some limitations with both areas that we need to address if we really hope to make a major dent. This just shows a picture taken a few weeks back when I had the opportunity to be in Brazil of sugarcane, and this shows truckloads of sugarcane coming into one of their it's actually the largest ethanol plant in Brazil. And in this particular truckload is machine harvested sugarcane, which is harvested by machinery going through the fields and loading up these these trucks where they pull in, excuse me, the whole plant, including the leaves and so forth. In the background in those piles is sugar cane that's harvested by people. In this case, they burn the fields first and then harvest it and stack it and bring it in. And this just shows one of the plants in Brazil. These are some of the ethanol fermenters that they employ to make ethanol. Just to give you a perspective on the size of these are very large fermenters that this picture fails to give you a real feeling for that. Also, as I mentioned, ethanol is produced from sugar cane or cane sugar in Brazil, and this shows on the left-hand side of this picture. And you can see that ethanol is produced or sold at a price considerably less than that of gasoline in Brazil. On the right shows a gas station in Denver and a Conoco station where E85 is sold in this particular case for $1.99 versus regular at that point in time, that was the spring, at $2.79. And in both cases, you're getting higher octane with ethanol than you are with gasoline, because it's important to remember that ethanol has an octane level of around over 100 versus gasoline, which is in the 80s. So in some ways, it's not totally a fair comparison, just strictly on price, but nonetheless, it's less expensive. But as I mentioned, my focus is really on cellulosic biomass. And the reason for that is cellulosic biomass is very abundant and quite inexpensive. And it's a word that's more well known now than it has been. Until January of this year, if you said cellulosic ethanol or cellulosic biomass, nobody knew what you're talking about. All of a sudden, there's a herd of experts out there. But anyway, what you find is you can divide it into two groups: existing resources, ag waste like sugarcane bagasse or corn stover, forestry waste, municipal solid waste, industrial waste. They're all categories that already exist that we could draw from for making ethanol and other products. Future resources are dedicated crops like herbaceous grassy materials like switchgrass, another plant that suddenly everybody knows exists. And you can have woody crops like poplar. But again, I'm not looking at sugar or starch crops as used currently. This just shows a picture of sugarcane growing in Hawaii, and this is a picture of sugarcane bagasse in Florida. And when you look at the size of this pile, you might think by the size of those telephone poles, that's not a particularly big pile. But if you look at the trees surrounding it and the building in the background, you see it's quite massive. And those poles have lights to shine down in the pile at night so they can stack up the pile during the night where they have bulldozers and trucks running up and down the pile. It's the highest point in Florida, no doubt. And here is a case of a rice hulls pile in Louisiana. And again, to give you some idea of the scale of this pile, this is just made from the little covering around a kernel of rice that's stripped off during rice processing and disposed of by dumping into these piles. And down the center of this, you can see roads that are used for tractor-trailer rigs to come in and dump their rice hulls onto the pile. And no doubt this is the highest point in Louisiana. We also have energy crops, as I mentioned. We have switchgrass on the left, we have hybrid poplar, we have willow on the right, all examples that we could use ultimately for producing fuels. Now the challenge is, we start with the solid material, but as I mentioned, we really want to make a petroleum substitute. So how do you put biomass into an automobile? Well, this is a good way to prevent the automobile from going anywhere, which certainly will cut its use of gasoline. But what we really have to do is figure out how do we convert that solid material into a liquid fuel. And we look at these different types of biomass, whether we're talking about ag residues like corn cobs or corn stover, or woody crops like poplar, municipal solid waste, paper, and yard waste fractions, for example, and herbaceous energy crops like switchgrass. They all consist of roughly 40 to 50% cellulose, about 25% to 30% hemicellulose, and the remainder primarily lignin, but other materials as well, oils and so forth. And what we can do is we can go through a conversion operation where we start with the cellulosic biomass shown here in green. We go through into the process boundary as shown by the dashed line. And at that point, we apply a pretreatment step to open up the structure to make it accessible to biological systems for conversion, because without that pretreatment step, our yields are very low. Then we go through the biological steps of producing enzymes, typically cellulase, but maybe hemicellulase as well, applying those enzymes to hydrolyze the cellulose and hemicellulose to sugars, and then ferment those sugars to ethanol. Then we go through an ethanol recovery operation shown in blue, but left behind now is a solid residue, the lignin plus any unconverted cellulose and hemicellulose, that we can then go on to burn to produce all the heat and electricity required to run the process, and actually have leftover electricity to export for additional revenue. Now, for relative metrics, a number of people have talked about this, so I'm going to be brief. But when we look at corn ethanol and cellulosic ethanol, we can see if we look at petroleum in versus energy out, it's very low ratios of petroleum use for either case. Corn is actually very low when it comes to petroleum use. When we look at total fossil energy in versus energy out, the corn uses considerably more other forms of fossil energy than it does petroleum, in the form of natural gas, possibly coal, and other feedstocks. But still, it's quite a bit better than if we use gasoline. On the other hand, cellulosic ethanol is also low here. And again, the key here is the fact that we can use the lignin to provide the heat and electricity to run the process. We use very little fossil fuel in the case of producing the biomass or distributing ethanol. We could actually use less. These numbers are, to me, somewhat based on worst case scenarios because they assume, for some reason, that the vehicles we use to produce and harvest and distribute ethanol are all powered by diesel. And why not use the ethanol we're making in the plant and get rid of those inputs? And why not use the methane that the plant produces during disposal of waste to make fertilizer to fertilize those plants? So you could use a lot less than these numbers show. And then if we look at greenhouse gas emissions versus gasoline, the fossil fuel numbers really are pretty much a telltale sign of how much greenhouse gas emissions you're going to get. And you can see, again, cellulosic ethanol does quite nicely with that regard. Another question asked yesterday was how much biomass is out there. And that's always speculative. We won't know until we actually get serious about this and do something on a large scale. But DOE and USDA recently put together an estimate that about 1.3 billion tons per year of cellulosic biomass could be available for making fuels and chemicals and power and so forth. And that's about 368 million dry tons from forests. And for some reason they came up with this 998 million, I would have called that a billion at that point. But anyway, tons from agriculture. So it's substantial. That translates roughly into about 130 billion gallons of ethanol, which is an appreciable amount of fuel. Now, the benefits of cellulosic ethanol technology are pretty well established, and I won't go into great depth about those, other than to say there's significant environmental advantages. One of those, I think, a key is greenhouse gas emission reductions. Another is economic, the fact that we can produce these domestically. And then, from an energy perspective, having a secure resource that we don't have to deal with politically volatile areas of the world. There's been significant progress in enzymatic-based technology for cellulosic ethanol. There's some debate about where we are now, and that depends on who does the economics, what technology they use, and so forth. But in general, we're competitive now in converting cellulosic biomass to ethanol with the cost of making ethanol from corn. And the key to those advances has really come from improvements in two basic areas. One is reducing or overcoming the recalcitrance of biomass. It's very difficult to break down biomass to form sugars. If it wasn't difficult, there would be no trees and grass. They'd all have been eaten by various microbes wandering around the environment. So it's taken some work to overcome that natural resistance, and that's through improved pretreatments, it's through improved enzymes, and it's through better integration of enzymatic hydrolysis and fermentation. Another key has been overcoming the diversity of sugars. One of the problems is in the case of cellulosic biomass, it contains 5 different sugars, whereas corn only contains 1. So we've had to develop organisms that can ferment all 5 sugars to ethanol with high yields, and that's been done. So if we look at the overall status of cellulosic ethanol technology, what we find is the operating costs are very low. We also find that, in my opinion, the technology is ready to be commercialized. The challenge is the capital costs are high. You don't get something for nothing, and the price you pay here is high capital costs. In addition to that, the cost of capital is high. Now, you might think, what's the difference between the capital cost and the cost of capital? But the cost of capital is what you have to pay to get money from investors to build something. And it's particularly high for first-of-a-kind technology. People don't give you money for something that's never been done before at the same rates they'll give it to you for something that's well established. And the complicating factor is the technology is not proven at a large scale. And that's really why the investors are reluctant to give you money at good terms. And on top of that, we have ethanol as a commodity product, which means it has relatively low returns. It's thin margins. So really what we have to be able to do is successfully predict the performance at a large scale to support these first uses. And one of the keys to me is understanding the technology better, and also to use that understanding to advance the technologies and reduce costs further. So if we look at how do we reduce processing costs, again, to me, biomass overall is a very low-cost feedstock, and it's competitive in price with petroleum. I'll talk about that a little bit later. But the challenge is how do we reduce the processing cost to be competitive without the need for subsidies, and biotechnology is a key opportunity here in that we have some very powerful tools to apply to reduce costs. And those lower costs will facilitate commercial use. And we did, a few years back, look at some advanced technology options in a paper where we looked at what was considered at that time NREL current technology. We looked at advanced technology that was judged to be feasible to do in a mature process, and then best parameter technology if we really got carried away with what might be possible. And what we found is that for current technology at that point in time, the predicted price was something on the order of $1.20 per gallon. Advanced technology that we thought was achievable was around 50 cents per gallon total cost, including return on capital. And the best parameter was something on the order of 35 cents per gallon. So what it showed, to me at least, was that low costs are feasible. Now, they're not simple, and it takes some really significant advances in technology to get there. And the key areas for really advancement are pretreatment and biological processing. Those are the two areas that we identified as requiring significant improvements in order to reduce costs. And as I mentioned, biological processing has a number of important advantages. That, first of all, it offers potentials of high yields that are vital to economic success. We cannot get good economics if we don't get high yields. And also, biological systems can take advantage of the advances in biotechnology. And then recently, there's been a couple of different, and others as well, initiatives announced on looking at funding development of better biological understanding and systems through, for example, BP has a program that they've announced, as has the Department of Energy for 2 centers for biological conversion. And both are focused on really looking at either the plants and the biotechnology of plants or the biological conversion systems. But the other thing we have to look at, though, is the central role and pervasive impact that pretreatment has for biological processing. It looks like it's just one chain and a series of other chains, but in fact, it has tremendous impact on everything else. For example, the choice of feedstock and the interaction with pretreatment are very critical to performance. Not all feedstocks do equally well, and there are some important synergies there that we have to look at. We also have to look at the effect of harvesting, storage, and particularly size reduction in its relationship to pretreatment. We have to consider enzymatic hydrolysis. Pretreatment can dramatically alter the amount of enzyme and the effectiveness of enzyme that we use. We have to look at hydrolysate conditioning. Pretreatment produces nasties that we have to get rid of if we want to biologically process the materials, so we also have to consider that. It has impacts on the fermentation step in terms of the mixed sugars produced and concentration of sugars. It has impact on ethanol recovery because the concentration of ethanol is directly related to pretreatment. It affects waste treatment in the sense of how much waste we produce, and the types of waste can be influenced by pretreatment. It also affects enzyme production. In particular, what mixture of enzymes do we need depends upon the pretreatment technology we select. And then finally, sugar fermentation is also impacted by the pretreatment step as well. In residue utilization, again, if we do the wrong things to pretreatment, we're not going to do a whole lot with those residues. On the other hand, if we treat them properly, we might get some value out of those. Another way to look at this is when we look at the various steps in biomass conversion, and we look at where we can have high impact in terms of enhancing yields or reducing costs, and I've shown those in green, and we look at those where we have a moderate impact, and then low impact, I've left white, moderate impact yellow, and then we see how does pretreatment cut across these. We see it impacts almost all of them. And so, again, it's important to not ignore the pretreatment step as part of the overall strategy. Another cut at this is to look at the key processing cost elements. And again, all costing in this field depends on who does it and a lot of other assumptions. So I wouldn't take any of these numbers to the bank. I have dealt with numbers that have been taken to the bank, and they work quite nicely. But I can't give you those numbers. But in the case of, whoops, not sure how I go backwards.
Escape. Top left. Escape.
I think
Okay, got it.
I think I got it. If we look at the cost elements, we see that the most important cost element is really the feedstock. It represents about a third of the cost. That might lead one to jump at improving feedstock costs, but when we look at feedstock cost, even though it's a third, it's really quite low. It's only, on a weight basis, only about equivalent to oil. This is plotting biomass feedstock costs in dollars per ton versus the cost of oil in dollars per barrel. And feedstock costing around $40 per ton, which we can get a lot of biomass at that cost, is equivalent to oil at about $7 per barrel. On a weight basis, I'm sorry, on an energy content basis, which is probably more accurate, even though that's somewhat lower because the fact biomass is oxygenated, nonetheless, it's still biomass at $40 a ton is equivalent to oil at roughly about $13 per barrel. So it's a very low-cost feedstock. So even though certainly it would be great to lower the cost, I'm not sure that's the best target. It's already pretty inexpensive. It's going to be tough sledding, and we might focus more on feedstocks from the viewpoint of how do we improve yields, drought tolerance, and those kind of things. So if we look at number 2 on the list, it's pretreatment, and number 3 is the biological systems of SSCF and cellulase production, SSCF being the combined operations of hydrolysis and fermentation. And so, again, we see the importance of really looking at pretreatment systems. I won't go through that one because I've already talked about that, but current and cost goal targets are presented here, and I'm not try to go through this in detail other than to say when we, again, line up all the process steps and look at where we are and where we might want to get to, what we find out is that a number of these areas are impacted by pretreatment, particularly the ones where we have much chance of making a major change. So if we further look at pretreatment, there are a number of key needs. First of all, we have to get high yields for multiple crops, sites, ages, and harvest times, and we've gotten data, for example, I'm involved in something called a Consortium for Applied Fundamentals and Innovation, which is among about 5 different universities. It includes University of California, Riverside, but also Auburn, Texas A&M, Michigan State, Purdue, and the University of British Columbia, as well as the National Renewable Energy Laboratory, in a cooperative effort to really, and I should also add Genacor International, in a cooperative effort to really improve technology and particularly focused on pretreatment. And what we found is significant variability even within the same type of crop. So it's very important to address that. We also have to have very high total sugar yields. That's critical. We need to reduce chemical use for pretreatment and post-treatment. Chemicals cost money, and even though sulfuric acid seems cheap, it ain't that cheap when you put it all together. Lower cost materials of construction is particularly a big issue. Eliminate hydrolysate conditioning and losses. We lose sugars during that step. Also reduce enzyme use. Those are expensive. We want to minimize their use. Minimize heat and power requirements and achieve very high sugar concentrations. So in closing, I'd like to offer that I think biology does offer a very powerful platform for low-cost fuels and chemicals from biomass, and it has a lot of importance to focus on improved biotechnology. And it can benefit both the crop production and the conversion systems, but we have to also consider that one system is resistant to the other. The biomass we produce is not particularly compatible with the biological conversion steps, and although we talk about improving plants so they're easier to convert, there may be a limit to that, at which point the plants are self-destruct in the fields and we don't ever get to use them. So we really do, I think, need to also consider the role of pretreatment in developing advanced systems that really will enhance yields and lower costs. And what we find is not all pretreatments are equally effective on all feedstocks. That's the point of this CAFE team I talked about. We've shown that fairly conclusively. And so focus on the 2 biologies without really integrating pretreatment in the equation will not necessarily lower costs. And with that, I'd like to acknowledge a number of sponsors who have funded my research, including the Ford Motor Company, who sponsors my professorship at the University of California, but also our partners from academia, industry, and government laboratories in a number of different agencies. USDA, DOE, and National Institute of Standards and Technology have funded our research. So with that, I'll close with this thought. Thank you very much.
Thank you, Charles, for an excellent presentation. We'll have time for two questions. We can start, Ilge. And Todd, you're going to be next.
First of all, I thought that was an excellent presentation. A lot of familiar themes. One of the things that we've been debating at Texas A&M and beyond is, and I don't think either one of us addressed in our presentations, was transportation. A lot of people are looking at switchgrass. For example, the Noble Institute and Ceres have announced a collaboration in genomics and switchgrass. What do you believe? Our estimates are you're going to need as much biomass as close to the conversion technologies, and those conversion technologies are going to have to be, for example, built in rural communities and have to build some pipeline to other existing pipelines. What do you feel about that?
You're talking transportation of the biomass, per se?
Absolutely.
Yeah, I think a couple of perspectives on that. One is, if you look, for example, I think you said sorghum gets 15 to 20 dry tons per acre per year?
Yes.
But if you take a number of 10 tons per acre per year, which is the DOE goal for things like switchgrass and so forth, or at least it used to be, and you assume you get 100 gallons per ton, which I think is very feasible with reasonable technology. So that means 1,000 gallons per acre. And if you look at a 50-mile radius, which is what people typically talk about when they talk about corn ethanol or pulp and paper plants and things that you go 50 miles to get feedstock. Well, at that productivity and yield, you can get 5 billion gallons of ethanol in a 50-mile radius. So it's pretty significant. And you know, somebody would say, well, you're not going to get all that because you have to have houses and roads and all these other things. Okay, so I'll cut it by 5. I get 1 billion gallons. It's still a lot. And you know, the other issue is things like, you know, the bulk packing density of biomass and all concerns about that. And you know, when I worked for BC International for a while to really design the first biomass ethanol plant. And one of the big concerns there, we were using sugarcane bagasse. And one of the big questions was, how much sugarcane bagasse can you fit on a truck? And we had people, all kinds of numbers about the bulk packing density of sugarcane bagasse. Well, we solved it the easy way. What we did is we rented a truck and loaded it up with sugarcane and weighed it. And it turned out you could get more on there than the legal load limit of the highway. So that wasn't an issue. So I think, in general, I guess I don't see those as major barriers.
I agree. It's a question that's raised all the time.
Yeah.
I thought I would introduce it.
Yeah, no, it's a good question, or a good one to bring up. And it's one of those questions that fits into the category of we keep going back and revisiting it. But
Okay, let's take another question. Todd.
I have a quick question, just a clarification. Thank you for a very nice presentation. Your talk was about pretreatment, but you never told us what pretreatments you would use. So I would like a clarification. Give us an example. For example, sulfuric acid, the cumulative free energy consumption is 70 megajoules per kilogram. That kind of puts it out of range here.
Yeah, I disagree with the last statement. The sulfuric acid is probably a leading option for it. But there are a number of other options, and that's what this CAFE project is about. And I didn't try to describe all the different pretreatments. I think it's good to look for more advanced pretreatments. But on the other hand, dilute acid has the advantage of you get very high sugar yields at a fairly modest cost. The biggest concern there is more to do with the chemical environment, the fact that the sulfuric acid requires or can require exotic materials of construction, and the higher pressures involved. Typically, you're talking something like 160 degrees centigrade. But in terms of energy requirements, you're talking about heating up biomass and the water with it to about 150 to 160 centigrade prior to processing. And those energy requirements, it roughly takes about 10 to 20% of the energy content of the lignin to do that. So you have plenty of energy left over after you burn the lignin for other purposes. So I don't consider it a significant energy barrier. And again, we've been through that when I just designed the BCI plant we had process guarantees and financing commitments from major banks based upon those kind of numbers.
Okay, thanks. Thanks again, Charles, for a very nice presentation. Let's move on now to look at a different option. Richard from the National Renewable Energy Lab is going to talk to us about thermochemical conversion technologies. Richard.
Good morning. Again, to echo previous speakers, I'd like to thank the Baker Institute for giving me the opportunity to talk this morning. And I'll put this up for a couple seconds and then we'll go on. What I'd like to do this morning, since this is really the only presentation that we have that is covering thermochemical conversion technology, and making the assumption that a number of you are not really familiar with thermochemical conversion, what I'd like to do this morning is give you a brief overview of thermochemical technologies. So more than anything else, that you're familiar with the nomenclature or the jargon that we use in terms of talking about thermochemical conversion. And I'm going to talk in thermochemical conversion about a different set of properties that are important for thermochem technologies, and then look at a little more detail about gasification, pyrolysis, and other technologies, some of which have been in the news recently. In the future, integrated biorefineries will involve both biochemical and thermochemical processes. This particular diagram reflects the view of DOE in terms of where it sees integrated processes going, where if a particular feedstock is amenable to biochemical conversion technology, it will be used for production of ethanol. Other feedstocks, such as lignocellulosic biomass that doesn't have the correct properties for high ethanol yield, or has, let's say, properties that are non-uniform, can be used for thermochem processing. Also, the lignin-rich residues that have been mentioned previously can be used to produce only heat and power, but at the same time they can be used to produce additional fuels and chemicals, either through intermediates such as pyrolysis oil and synthesis gas. So, when we look at thermochem conversion, we have a number of primary conversion routes, and each of those conversion routes gives us a different types of products. So everybody's familiar with combustion. Combustion really just produces a hot gas, and then we use that hot gas to make electricity, make steam, make hot water. In gasification, we go through and we do a partial conversion of the biomass, and in that case what we do is we make a set of combustible gases, or gases then that can be further converted into fuels and chemicals. So if you look at gasification as an example, when you talk about biochemical conversion, what you're doing is you're going through and doing a partial conversion of the biomass to produce a desired product. In the case of gasification, what you do is you go through and you completely break down the organic structure into its simplest constituents, and those constituents are hydrogen and carbon monoxide. Then you go through traditional synthesis chemistry to go through and rebuild those molecules back up into products that you want. Looking at partial conversion of biomass, then you can also go through and you can do pyrolysis, which then is a partial conversion. And in that case, you make an oxygenated oil, which typically needs further refining to make your desired products. So, what kind of products are we talking about in terms of thermochemical conversion? Well, fungible fuels and chemicals are the major products. So we're looking at products that are commercial products in the marketplace today. New classes, such as oxygenated oils, will require market development. So again, in gasification, typical products are things such as hydrogen, alcohols, including ethanol, Fischer-Tropsch liquids, gasoline and diesel, olefins, oxochemicals, etc. In the pyrolysis area, we can take that intermediate oil and we can convert it to hydrogen, olefins, specialty chemicals. And then there are other conversion processes that include things like liquefaction or hydrothermal conversion, which again make an intermediate oil product that is typically further converted into final products. Okay. I am an engineer, so I like flowcharts, by the way. But for this audience, at least I did look through, and I didn't put any equations in, so it's not as bad as it could have been. In thermochemical conversion, we're looking at primary, secondary, and tertiary reactions. So primary reactions involve the initial heating of the biomass and conversion to primary liquids and gases and solids. Secondary processes involve then conversion mainly of the primary vapors to intermediate compounds such as olefins, aromatics, and permanent gases. And then if we're looking at gasification, what we want to do is look at tertiary products that then take these intermediate contaminants, if you will, and convert them to a final simple gas, which is typically rich in CO and hydrogen. Okay. So in order to understand thermochemical conversion, we need to go through and know the physical and thermal properties that influence thermal behavior. So we talk a little bit of a different language when we talk about thermochemical conversion. So typically when you're talking thermochem conversion, we're going to talk about proximate and ultimate analysis, and we're going to talk about the composition of the ash. We're going to talk about heating value. Those are the things that we really are important in understanding thermal conversion. So biomass is different than traditional fossil feedstocks. So what we do in doing approximate analysis is we go through and we look at the amount of volatiles that can be driven off when you heat up an organic material at a set of fixed conditions. And typically what we see for something like coal, when we look at approximate analysis, is that it contains about 50% fixed carbon. And the fact that it contains 50% fixed carbon dictates how we can process it. Whereas biomass contains about 80% volatile matter and only 20% fixed carbon. So in many respects, biomass gasification is simply a devolatilization process. It is not a fixed carbon gasification process, if I can design the process correctly. If I look at the ultimate analysis, which just gives me the elemental composition of biomass, I look at carbon, hydrogen, nitrogen, oxygen as the primary components. Sulfur is also important, but with biomass, sulfur is normally pretty low. And when we look at the composition of biomass, we see that it is very high in oxygen compared to fossil fuels such as coal. Typically, the sulfur content of traditional biomass is very low compared to fossil fuel. If you're looking at various types of residues, and in this figure, what we did is we used chicken litter as a residue, and we used black liquor as typical of a different type of residue. In both of those cases, we see, because of the processing that we have done, that we've increased nitrogen content and sulfur content, and both of those are important in terms of how we go through and do thermal conversion. So those elements in there, typically what you see then is because of the high oxygen content, is that the heating value or the heat content of biomass is substantially lower than it is for something like coal. I didn't put it on this chart, but that in combination with the fact that biomass has a low density means that transportation costs are relatively high compared to fossil fuels because we have a low heating value material, low density, and it's more expensive than to transport it. In addition, we also want to look at, since we're heating things up to a high temperature, we want to look at what is in the ash because that impacts how we can process it, because things in ash tend to melt. So we look at things like alkali content. We look at sodium sulfur composition as being indicative of what kind of temperatures that we can operate at or what kind of process we have to design. Gasification has a long history, not as long as combustion, of course, but which has been there forever. But gasification has a long history of development, so it's over 200 years old. In terms of a couple of the highlights, most of what we would consider modern technological development took place in the 20th century, most of it in Germany in the early part, before World War I. And I think what they call vehicle gasogens during World War II, biomass has been used as a transportation fuel if the circumstances are right. So in World War II, there were over a million vehicles in Europe, primarily in Germany, Sweden, that actually had little biomass gasifiers where you came out in the morning, you put wood in the gasifier, you started heating, and then a half hour later, you were ready to run, and so that you could drive your vehicle. And typically, a dirty gas, the engine didn't last that long, but somehow there were travel restrictions then anyway. So, and I think we also see that gasification-based systems have been used for both in South Africa for production of typical refinery products. We're looking at gas to liquid processes now, and potentially it's a good method of making hydrogen in the future. Gasification-based technologies are commercial technologies today practiced at large scale. The syngas market, which is CO and hydrogen, is approximately 6 exajoules per year. To put that in context, that's comparable to the total renewable energy production in the United States now. It's also comparable to what is being done in Europe today. The primary products that you see are, number one, ammonia, and number two, hydrogen, primarily for use in refineries, and methanol. And methanol markets historically have been for MTBE, but the other major markets are for things like formaldehyde production. Let's see. This is the world of gasification, and I tried to make it more complicated, but it was hard to make it more complicated on one slide. But let's go very quickly through gasification-based process. You have really 3 steps that you're looking at when you want to produce a liquid fuel via gasification. You have the primary conversion step, a cleanup step, which involves tar removal and syngas conditioning, and then a final step, which involves rebuilding the molecule back to the product that you want, and we call that biofuel synthesis. Again, gasification processes are generally tailored to the feedstock, and again, biomass has 80% volatile matter, so we can go through and we can do low temperature steam gasification. At the same time, there are a lot, the existing technology that's out there that I showed previously is based primarily for things like coal and petroleum coke, materials that are hard to convert. In those cases, what we do is we use very high temperature. So what we do is we look at temperatures around 1400 degrees Celsius, and under those conditions, the ash melts. So we have what we call a slagging gasifier, which means we want to take out a molten inorganic plus the gas. In the case of biomass gasifiers, which can run at 800 Celsius, we may have a dry ash, but then we have different contaminants for each of those. The problem with the existing industry that's based on coal is it requires a very small particle size, and that's hard and expensive to do with biomass. So what we do in that case is we go through a pretreatment process, if you will, which typically involves pyrolysis to make the material easier to feed to these high temperature gasifiers. Then we go through various types of cleanups. There's always some residual particulates in a system. If we're going to make fuels, we have to get rid of all of the sulfur. If the gas composition, this carbon monoxide and hydrogen ratio isn't correct, then we have to go through and we have to adjust that composition. We have to remove any, let's say, things which are considered hazardous or detrimental to the catalyst. So you have things like heavy metals, cadmium, you have mercury, things like this that you have to remove. Then once we're done, we can go through and, in essence, make whatever type of product that you would like. There are a lot of companies that go through and have developed biomass gasification systems, and I just gave, well, in this case, this is thermal conversion systems, so I've also included pyrolysis. You can, and this is just representative of the companies that are looking at gasification development, and I have not included the companies in here who have gone through and developed commercial fossil fuel-based gasification systems. But again, we go through, and to classify systems, we look at temperature and pressure as our variables and try to go through and talk about companies who are working in a certain area. Even though we are talking about fuels and chemicals, traditionally biomass gasification at small and medium scale for combined heat and power is a good opportunity. And I think examples are a small company that's based in Colorado called Community Power Corporation, which is looking at small combined heat and power systems at about the 25 kilowatt electric scale for use on, initially it was being developed for use in villages in developing countries. It's also being looked at for institutional use. There is one demo project going on where they're using CHP at a high school in Colorado to provide heat and electricity for a greenhouse. Combined heat and power systems for district heating is a very good opportunity and is very attractive in Europe, where they give you good incentives for doing those types of things. So the system that was shown here is about a 5 megawatt electric system that also provides hot water for about 2,500 homes. And then what we're starting to see is a number of projects in where people are starting to use biomass gasifiers for CHP in corn ethanol facilities. And the one that I put up here is in Minnesota, where they're using about a little less than 300 tons per day of wood to provide the electricity and heat for a 15 million gallon per year ethanol facility. Transportation fuel systems are going to be at larger scale because the process is substantially more complicated, and I threw up a somewhat typical schematic of a thermochemical conversion process to produce ethanol. There may be opportunities for smaller modular skid mount type of systems. But today, most people are looking at central production facilities just because of the scale that you need to look at. Fungibility is going to be a key to success. And this figure was originally developed by BP, but I think it brings home a couple of good points. And the first thing is that if you go through gasification, you make a fungible product. So once you get to syngas, the properties of the syngas are independent of the feedstock. So we can make the same syngas from biomass that you make from coal, that you make from natural gas, you make from heavy oil, you make from tar sands. And I think if you look at it and we go through and if we go through and we look at the environmental impacts, that I think, as a number of speakers have said, when we're looking at fuels, if we're in a carbon constrained world, then biomass is a premium feedstock. So if you have things such as carbon credits or CO2 penalties, then yes, biomass is a premium. From a perspective of a company who really is in the business to make money, if you look at the gasification route, then what you have is you have flexibility for the future. And if you're carbon constrained, you can use biomass. If you're not carbon constrained, then you can emphasize the fossil fuels instead. The types of products that, again, we have said this before, that you can make, again, are things like Fischer-Tropsch liquids, methanol as an intermediate to other products, or as a product by itself. The emphasis of the DOE program right now is primarily in terms of ethanol via a mixed alcohol synthesis process, where mixed alcohol synthesis typically takes a Fischer-Tropsch catalyst and adds some type of additional reactant so that you can make alcohol rather than a traditional diesel type of fuel. Another product that is being looked at very heavily in Europe as a potential cold weather diesel fuel and as a substitute for LPG is dimethyl ether. And dimethyl ether is more commonly, the only use that I know right now for DME is it's a propellant in hairspray. So if we look back to where we started at the beginning in terms of gasification, this is an example of what we would think as a second or third generation advanced integrated biorefinery, where again the primary conversion process is biochemical conversion to produce ethanol. A portion of the lignin residues are used for CHP in the process, and the remainder of the lignin residues are taken to a selective thermal processing step where we specifically have, or on purpose have not gone through and really defined the process for you, where the product is not additional ethanol, but the product is directly gasoline. So coming out of one facility, you can make an E85 type of product that requires no additional blending in terms of the distribution system. There's been a lot of analysis done on the years for thermochemical conversion technologies. Back in the early 90s, there was a lot of looking at methanol Fischer-Tropsch liquids. Today we're concentrating on alcohols, but I think this type of figure tells you some interesting things. First of all, it tells me that it's a capital-intensive process. We're looking at capital investments, and I put them in dollars per gallon of methanol. Per annual gallon of methanol, for people in the petroleum business, we would typically go through and do it in terms of dollars per daily barrel, but this is comparable to what's used in the ethanol industry in terms of dollars per annual gallon. So looking at projected capital investments, we're looking at numbers in the $1.50 to $2 per annual gallon. Indirectly heated gasifiers are steam gasifiers. Traditional biomass oxygen-blown gasifiers have costs that are a little higher, and there's a lot of discussion on whether we should be using slagging gasifiers that have been developed for coal. What these numbers are really telling us is that at 2,000 tons per day, we would typically be seeing for biomass 4,000 to 5,000 barrels per day of product. And something like coal slagging gasifiers are being optimized for scales that are around 30,000 barrels per day. So if we try to scale down those systems, we're not at least right now, we're not at the optimal point that we need for those. So in terms of looking at first and second generation development, really what we're looking at is looking at right now that the economics say it's probably better to go through and to look at gasifiers that are specifically developed for biomass rather than coal. That doesn't mean that we won't do it in the future, but there's a lot of work in terms of scaling down and still staying economic. If you look at the mixed alcohol process, and we can look at that in the context of the DOE goals for ethanol, that the numbers that we get for ethanol from the thermochem route versus the biochem route are comparable in order of magnitude. And that's, I think, what it's telling us is that there are a lot of the variables that go into the cost are actually independent of the process. They really are. That's things like the feedstock, cost of utilities, things of this sort. You see that the yields are lower than what we would see for an ethanol-only process, around 70 gallons per ton of ethanol, but at the same time, there's another 20 to 25 gallons per ton of higher alcohols, things like propanol, butanol, that are coming out of this type of process. Okay. The second area is pyrolysis. Pyrolysis is thermal decomposition of organic matter in the absence of oxygen. It's always the first step in a combustion gasification process. So if you go through and you have a fireplace and the smoke that's starting to come off of the wood is a pyrolysis vapor before it's burnt. It's been known for thousands of years. Slow pyrolysis is been used for producing charcoal. If you want to maximize liquid yields, you heat it up very quickly and cool it down very quickly, and you get about 60 to 70% oil. And this just kind of compares carbonization, low heating, high solids, low oil, fast pyrolysis, high oil, low solids and gas. We're at about 500 C. How much time?
A few minutes.
Okay. And then gasification, you're doing the same thing. You're just heating it up an extra 200 degrees Celsius, and now you make about 85% gas. Oops. There are a number of very small commercial units operating for pyrolysis, primarily to make boiler fuel. I think there is a 1,000 kilogram per hour at Red Arrow in Wisconsin, which makes something that a lot of people are familiar with. They use pyrolysis to make liquid smoke that you can use then as an additive when you're doing barbecue. So I don't use liquid smoke myself. I know too much about pyrolysis, but it's... So what do you make? You make a dark brown viscous liquid. It's not miscible with hydrocarbons. Its elemental composition is almost the same as what you started with. So some people actually call it liquid wood because its composition is the same as the starting biomass. It's just undergone a small amount of depolymerization. The heating value is again comparable to the starting material on a weight basis. On a density basis, it's much higher than the initial starting biomass. It's heavier than water, so that if you put it in water, what doesn't dissolve is going to sink. It's very acidic, so it's got a pH of about 2.5. It's got a very distinctive, strong odor, and because of the high acidity, it tends to age with time. So because of those properties, people are looking at upgrading it and doing different things. So there are a number of applications. The simplest application is simply to use it as a boiler fuel. That's been done. People have looked at using it as a diesel fuel with some success. And people have been looking at extracting chemicals. My example was liquid wood, but you can also extract phenols for use in things like phenol formaldehyde resins, which they use as an adhesive in things like plywood, or you can upgrade it to make transportation fuel. So what we would do, one of the things that's being looked at right now is you've got to improve those properties that I said was bad, and still got a lot of oxygen in it. Oxygen is, if you look at transportation fuels, if you look at a traditional petroleum-derived gasoline or diesel, they don't have oxygen. So we need to reduce the oxygen. We don't need to make it zero, but at least need to reduce it. One thing that's being looked at is to go through and take a certain portion, which is the pyrolignin, the lignin-rich fraction, and feed that to either a cat cracker or a hydrotreater in a refinery, and then doing something with the residue. So this would be an example where you go through and you make a gasoline blend stock from the lignin fraction using something like a hydrotreater, and you look at the water-soluble fraction and go through some kind of a fermentation process. Switching to and right now what I'm doing is just going through and very briefly touching on a couple of processes that you may be hearing about. One would be to take the fatty acids that we've been talking about in terms of making biodiesel, and taking that same material and feeding it to a petroleum refinery to make a high-quality diesel blend stock. And the reason that's being looked at is it does have the potential for lower costs, both operating and capital costs, than biodiesel, and it also makes a product which is superior. In the following respect, it's material that has a density that's a little lower than something such as FAME. Sulfur content, of course, is dependent on the feedstock, so it's about the same. Heating value substantially higher than biodiesel. NOx emissions versus a traditional diesel are typically lower than traditional diesel. Cloud point is comparable in the range that we'd like to see for a diesel. The distillation curve is comparable to a diesel, and the cetane number is in the 80 to 100 range. So that sounds like an attractive process, and it's something that people are considering, because you're starting with the same feedstock, and you're ending up with the same class of product. And a number of petroleum companies are looking at doing this commercially. And Neste is building a commercial plant in Finland for about 170,000 tons per year of product, and it's been tested at a commercial scale in places like Ireland. It's not being done in the US because green diesel doesn't get the excise tax credit. One more, this is the last slide. And the last area is hydrothermal processing or hydrothermal treatment. And it is used to make primarily liquid products, which can again be upgraded to substitute for standard petroleum products. There are companies such as Changing World Technologies has been in the news a fair amount in terms of processing poultry wastes to make oil, and it's being looked at in Europe also. So hydrothermal treatment is really fairly simple. What we do is we're going to mix the biomass plus water, plus maybe a catalyst such as an alkali, sodium carbonate or something like that. We're going to heat it up to 300 C under enough pressure to keep all the water as a liquid. We're going to hold it there for a few minutes, and then we'll typically flash off and separate the oil and water. And yields are high, the distillate yield is reasonable, but it's not a fungible product at that point, so it does have to be upgraded. Suffers from the fact that it is, when I say sufficient pressure to keep water in the liquid phase, we're typically talking 1,500 to 3,000 PSI. So it is a it's a capital intensive process again. Okay, so thank you. Thank you for your attention.
Thank you for a very nice presentation. Are there any questions? Yes, Sergio.
Yeah, very quickly. At what stage of the refining process do you introduce the greases and vegetable oils that you just described?
Typically, it's put into a distillate hydrotreater. There's some consideration of using a separate skid mount unit so that you can optimize the hydrotreating catalyst specifically for the oxygenated material. Right? One of the keys to the economics on that is going through and you have to remove oxygen, so you can either remove it as water, which involves hydrogen, which is expensive, or doing a decarboxylation where you remove some of the oxygen and carbon together as CO2.
Yes, Susie.
I liked some of the characteristics of your green diesel, especially in my area of the country. It would be much more effective in winter than biodiesel. My question is, are there any ASTM standards or any sort of, for the green diesel that are comparable to the transesterification biodiesel?
In the case of going through and looking at something like green diesel, you're going to use the standard commercial specs, the ASTM specs that are used for a standard petroleum diesel. If we looked at if we wanted to make something like a JP8, you could use something like the military specs for JP8. You could also, they can tailor it to do that also. So it's just going through and doing. There was a set of ASTM specs that was in EPACT for renewable diesel, which was separate than biodiesel. That same set of specifications can be used for this product.
Thank you. Thanks, Greta, for a great presentation.